Today we are going to simulate a step-down chopper or a buck converter. So this is the circuit which we have realized in the class, wherein we have a input DC source, then we have a semiconductor switch. It's considered as an ideal switch. Here we'll be using, instead of a switch, either a power BJT, power MOSFET or a IGBT. So in today's simulation we will be using power MOSFET. So here we have a diode, then an inductor, filter capacitor, and a resistor, load resistor. So we will be implementing this circuit in eSim. Now, eSim is an open source EDA tool for circuit design, simulation, and analysis, right? And it is integrated with various open source software such as KiCad, Ngspice, GHDL, Verilator, MakerChip IDE, and Skywater 130 PDK. Right. So, and it is released under GNU General Public License. Now, to create, first of all, to simulate the circuit of buck converter, we have to go over here and click on new project. Here we can give the name of the new project as buck underscore converter. See to it that no spacing is given over here. I'm calling it new. So buck underscore converter underscore new is the project name. Then I click on OK. So a new project name will appear over here, and from here now you have to make the schematic. So click over here and click on open schematic. So it does not exist, the schematic does not exist. Do you wish to create it? Yes, you have to click on yes. So a schematic window will appear. Yeah, so this is a schematic screen in eSIM, and from here we have to select the components and start making the circuit. So let us do that right away. Now I can maximize the screen. Yeah, so go to place components, click over here, and then click anywhere on the screen, and now you can type the components, right? So you can type DC source. So this DC, capital DC, you have to select and click on OK. So to place the component, just click, mouse click, right, either left or right. Now again go to place component. Next we have to select is, see over here, instead of a switch we will be using a MOSFET, right? So we have to select a MOSFET. So here I'll type eSIM underscore MOSFET n type. So this is n channel MOSFET which I'm going to use it. So this I'll place it onto the screen. I can maximize it so that I can view it like this. Alright, now I can rotate this component. I can orient it. I can rotate it counterclockwise. Yeah, we have to use it in this form. So that's why I've kept it over here like this. Fine. Okay. So the next component in a buck converter is, and also we have to give a gate pulse, right? So that we will decide. Next is diode. So again, I'll click on the component eSIM diode. So here I'll place it over here. Remember, again we have to rotate this. So orient clockwise. Yeah. So this component is also placed onto the schematic. Okay. Next we want is inductor. So you will click over here, eSIM underscore L, inductor. So we'll place the inductor over here. Let's say over here, right? Now we require capacitor. So eSIM underscore C, capacitor. Click on OK, and you can place it over here. And finally we require a resistor. So you can type eSIM underscore R. Yeah, so this is my resistor. Now I have to orient this resistor. I'll do that later, but first I'll place it, then right click, orient counterclockwise. Yeah, so I have placed my resistor also onto the schematic. Now I have to join them, connect them all together. So I'll use this wire. This is place wire. So I'll make the connections, click, and again click, right? So this way you can connect all the components. So I'm connecting it to the capacitor, then the inductor, yeah, then from the inductor to the MOSFET like this, and then the diode connection, then the resistor connection at the output load connection. Okay, so the connections have been done. Now the substrate terminal or the body terminal of the MOSFET has to be connected over here. So I'll connect it over here, right? All right. So the circuit is made now, and we have to just add a pulse source because we have to apply a pulse at the gate of the MOSFET. So for that, again go to place component, click over here, and we have to type pulse. eSIM sources, under eSIM sources you will have pulse. So click on OK. So you can place the component like this. All right. Yeah. So now I'll connect with a wire. All right. So this has to be connected now. We have to connect the ground also. So I'll go over here and I type eSIM underscore ground. So this ground I have to add it, let's say over here. All right. Now this pulse source will be going to the ground, so I'll be connecting it over here, and this ground has to be connected over here like this. Fine. So all the circuit connections have been done. Now I have to select the values. So select the values for right now for the DC source, for the pulse, we will select them while doing the simulation. Now for the value of L, I'll right click over here. Oh, sorry for that. I'll select this, and now I'll right click, edit value. So here I will edit this text and I'll enter the value as 1.5 millihenry. So its value is 1.5 millihenry. Again I'll go over here. So let me check the circuit. Yeah. So it has to be 1.5 millihenry. I'll right click over here, edit the value. Capacitor value we have to take it as 10 microfarad. So I can type over here 10 U. So U stands for microfarad and click on OK. By default the unit will be in farad only. Now next I have to select is the resistor value. So R value is around 500 ohms. So I'll go over here, right click, edit value, and enter 500 ohms. Okay. So now my all the components have been taken care of. All right. Now I will define the label, that is the global label. That is when we plot we require the label reference. So label have to be given from this place global label. So I'll place one over here for the input. Okay. So let me say we will require label for the input. We'll require label for the switch voltage. Then we'll also require the label for the output. All right. So I'll go over here, place the label and enter as in. Okay. Now orientation I'll keep it as right and the shape is input. So I'll place the label over here and then use the wire to connect it over here. So this is my label. Oh, sorry for that. Yeah. So this is my label. Again, I'll save the schematic. Now also I required a label for the switching voltage. Let's say if I want to plot switching voltage also. So again I'll go over here. Then I'll type VSW switch voltage. Again it's the input, and I place the label over here and then use the wire to connect it. Okay, so this has been done. Now at the output also I'll require a label. So again I'll go to the global label, click over here, and here I'll type out. But here the shape will be outside and the orientation will be left. So this is how I'll place the label, and then I'll click on the wire. Yeah. So the label placement is done. The global labels have been added. Now what all plots I require, right? So first of all, I'll require the plot of the, let's say we will have to plot input also, let's consider. So there I'll go again to the library, click over here, and I'll type plot V1. So plot V1 is for plotting the voltage. So I'll click on OK, and I place one plot probe over here. Okay, I'll connect it with a wire. So this will plot my input. Now let's say I also want to plot my switching voltage. So again I'll go to the place component. There I'll select plot V, click on OK, and I'll add one plot over here and then connect it with a wire. So whichever value, whichever quantity you want to plot, we have to add it like this. Now I also want to plot the output. Alright. So for the output I'll require again a plot V1. Oh, sorry. I will let's say it has gone out of bound. I'll bring it back. Okay, fine. So I'll select output, and here will be the plot, and I'll connect it with a wire. So this will plot the output. Now additionally I also want to plot the current flowing through the inductor and the output current. So for that, for placing the current probe, we have to place it in series, right? So first of all, I have to delete this wire. So right click on this wire and delete the wire, right? So actually this also got deleted. So I'll connect this back. Okay. Now I have to place a current meter over here. I mean the probe which can measure the current. So I'll close this. I'll again go to place component, and there I'll plot I, plot underscore current I2. Alright. So plot underscore I2 will we can measure the current through the node. So here it is. I'll place the probe over here and then connect it with the wire. Similarly, I have to plot the output. So I'll right click, delete the wire first. This also got deleted. So again I'll go to place component and plot I2 because I want to measure the output current, and then I'll connect it back with the wire. Okay, so what all quantities we will be observing? We will be observing V in, then the switching voltage, then the current flowing through the inductor IL, and the current flowing to the output that will be in series with it. Alright. Okay, so yeah, so let's continue with our analysis. Oh, sorry for that, I'll cancel it. Now further, I have to, my circuit is ready, and now the next thing is we have to go to generate the netlist. So click on generate netlist, go to Spice, click on the default format, and click on generate. So when you click on generate, it will ask for the location. So you can give, you can save it in the eSim workspace and click on OK with the save name. Now it will ask you to annotate the circuit. So annotation is required, right? So just click on annotate. Click on OK. Yeah. So you see all that were question mark before. Here it was a question mark, right? So it has become L1, C1, R1, right? Proper annotation is given now. Alright. So the circuit is ready for the simulation. So for the next part, we have to just save the schematic and minimize this. We have to go to eSim now. Okay, so here our schematic is created. If I right click over here and refresh it, as you can see, the new schematic is created. Now we have to set the simulation parameters. So click on convert KiCad to Ngspice. So here I have to give the simulation parameters. So we will be doing the transient analysis. Let us say the start time will be 0. Step time will be around 100 microsecond. So I can select the unit over here, 100 microsecond. And the stop time will be, let's say, around 12 millisecond. So all the parameters I have given over here. All right. Next, I have to give source details. So source details for V1. So this is my V1, right? V1 is my input DC voltage. So the source details for the input DC voltage will be around, let's say, 15. No need to give the unit. It will take by default as volts. Then the pulse. We have to give the pulse to the MOSFET, right? So that it switches on and off. So here I can give initial value as 0, pulsed value as around, let's say, 20. Delay will be 0. Rise time will be 1 nanosecond. Fall time will be 1 nanosecond. Pulse width. Now in a buck converter, we know that. Let me go back over here. We have seen that before in a buck converter. Actually, we have derived it also. The output is related to the input with the duty cycle. So let's say if the duty cycle is 50% and I've given input as 15 volt, my output will be around 7.5. So that's exactly what we are going to do. So we have to going to set the duty cycle. So how to set the duty cycle? So duty cycle will be T on upon capital T. So let's say that if I give the on time of the pulse as 5 microseconds and the total period as around 10 microseconds, then my duty cycle will be 50%. So that's exactly we will do over here. So we'll give the pulse width as 5 microsecond and the total period as 10 microseconds. So that means the duty cycle is 50% now. If I would have given over here 4 microseconds, the duty cycle would have been 40%. So let me give 5. Okay, so let us go to the next option. There is no Ngspice model for this. Then for device modeling, we will be adding a library over here. So here we will have a eSim NMOS transistor. So for the eSim NMOS transistor, we'll click on add and here you will see MOS. So in the MOS, you will select NMOS zero point 0.5 micrometer. So NMOS zero point 0.5 micrometer will click on open. All right. Let us Yeah. So we have added the NMOS model 0.5 micrometer library. Here we have to give the width as, let's say, 100 micro and the length will be around 0.5 because it's 0.5 micrometer technology, and your multiplicative factor will be 1. Now we have to add the model for the eSIM diode. So I'll click on add. I'll go to the diode and I'll click on this. We can click on power diode also. That's absolutely fine. Okay. And I click on open. All right. So now sub-circuit model is also not there. So device modeling, source details and analysis. All the details are filled. Next I click on convert button. So your KiCad is converted into Ngspice successfully. I'll click on OK. Now I'll go over here and click on refresh. So as you can see, lot more parameters or lot more files have been added over here. Now for simulation purposes, what we have to do is we have to click on this tab over here, simulate. So let us click on simulate. It will take some time. Yeah, so we are getting the simulation parameters one by one. All right. So here are the simulation parameters which we are getting. Let us check them out. Okay. This is around 12 millisecond. I guess in device modeling, while adding the diode, we have to add, let's go back over there and add the normal diode, D library, not the power diode. Power diode is a little slow. So let us convert that again. Okay, let us rerun this step. Again, I repeating, when we add the diode model, you select the diode, D library. So I'll convert it. Okay, now I'll refresh the project. So now again I'll go to simulation and click on the simulation. So the plot will appear. Okay. Okay. So earlier we have changed one thing. So basically in a schematic, the diode which we are using, if we use a normal diode, it's very slow. It cannot keep up with the chopping frequency, right? So we have to select a Schottky diode, or we have to select a fast recovery diode for a buck converter. All right. So what we will do is we'll go over here, and in the device modeling, when we add a diode, we have to select the Schottky library. All right. So please select the Schottky library, and then you can go to the analysis. Again, click on convert. Then right click over here, refresh, and click on the simulation button. It should give you the results in no time. So this is my input, this is my switching voltage, and that's my output. All right, great. So here I can check the values. Now this I of V4 is basically the output current, right? The output current flowing through the load. Then next plot we have it is U3. So this is basically the current flowing through the inductor. Now current flowing through the inductor is actually triangular, right? Like a triangular waveform. So here we will maximize this and see. So to maximize, what we will do is we'll right click over here and drag it to this part like this. So it will open a new window. All right. So as you can see here also we can maximize, right click and drag it to that limit to that window. So as you can see, you're getting a triangular waveform, and it's following CCM because I minimum is greater than 0, continuous conduction mode. So buck converter is following CCM since I minimum is greater than 0. So this plot we can have to, this way we can maximize and show the plot. All right. Now next plot is about, I mean, this is the transient part and this is the steady state part. So up till 1 millisecond, we will have the transient part, and after that we will have a steady state part. Then for the output voltage, right, this is the output. All right. Ideally speaking, for the duty cycle of 50%, input being 15 volt, output should be around 7.5. So let us observe if it is around 7.5. As you can see, up till 1 millisecond, we are getting the transient part. After that, we are getting a steady state part. So I'll right click and then add it over here. As you can see, it contains small amount of ripple. Yeah, here it is. So here I can maximize this further. Okay, so here we are getting the output ripple, and its value is around 7.25, between 7.25 and between 7.246. That's absolutely fine because we will, in this, if we would have used the actual power MOSFET, then the results would have been much more nearer to what we are getting over right now. All right. So these results are also absolutely fine. This is the this is validated because around, it should be around 7.5, and we are getting close to around 7.5, that is 7.25 to 7.46. So this we have to take the uh, you know this is how we can get the output. Now I'll close the windows. Now this actually shows in black screen. If I have to change the color, what I will do is I'll do the following. I'll go to my eSIM window. Here also we can plot our, here this is a Python plot. So let's say if I want to plot my output. So I'll click on the output, click on plot, and here is I can get the plot, right? So here I can expand it also. It will give me the value, right? As I further expand it, further expand it, further expand it. So this way also we can have a Python plot, and you can just directly save this folder, save the image, and directly have it in your write-ups. All right. So this option we can also use it. Right now we are not using it, but you can also use it. Now to change the coloring, right? So go over here, and here we have to type certain statements because the background color in Ngspice is coming out to be black. So that's why we have to change the color over here. So we have to write a statement over here: set color 0 as let's say white, then set color 1 equal to let's say black, and set color 2 equal to blue. Okay. And also there is one more option to check the you know the width of that output waveform. It was very thin, so in order to make that thick, we can do the following. We have to set as something as follows: brush width. Okay. So set x brush x brush width equal to, we can select equal to 3, and color 1, color 2, color 3, white, black and blue, and set brush width equal to 3. Now I'll click on save, and then I'll again click on the simulate button. So right now the plots we will get is with the white background, as I can see. And I mean, this is how we can change the background. All right. So we can get all these plots. Let me show you to you by maximizing this one of them. So how clearly we are getting it. So right click, I'll drag it. So this is the waveform I'm getting, current waveform across the inductor. I can further expand it. Yeah. So this is the way we have to plot. You can simulate it. Don't take black screen because while printing that will create problems. So you can set the color like this, as I have shown over here. All right. So this completes the simulation of, we have verified the output, right? So what you can do is, next time is, if you want to change the duty cycle, what you need to do is go back to the, again you can go back to and keycat to Ngspice, and over here in the source details we can give around, let's say, 4 4 micro 4 microseconds and 10 microseconds. That means 40% duty cycle. So 15 into 40% duty cycle will give you around 6 volts. Should give you around 6 volts. I'll click on convert. I'll click on OK, and I'll click on refresh. So for the 40% duty cycle, let us observe the waveforms. It should be close to 6. Let me close the old waveforms. So lot where windows were open, so that's why I think we'll close them all. And now we will be plotting it again. Yeah, now it will come. So right now for 40% duty cycle, again we have to set that this thing. We can set so every time we have to plot, we have to set the color as we have done before. So right now output over here, as you can see, if I expand it, let me expand it from here, and so as you can see, output is around 5.875. It should be close to 6, but that's fine. We are not using a power MOSFET over here, so that's why the deviation is slightly there. So if I expand it further, the variation is between 5.877 and 5.874. This is the amount of ripple which we get at the output. All right. So just by changing the duty cycle, again I repeat, where we are changing the duty cycle, we were changing the duty cycle in source details. So by changing the pulse width, Let's say if I want to give 60% duty cycle, I'll write over here 6 microseconds. All right. So in this way, we simulate the buck converter or a step down chopper simulation. So yeah, so thank you everyone for watching the video, and yeah, and I recommend to use eSIM a lot more for circuit simulation. All right, so thank you. eSIM was developed by eSIM IIT Bombay FOSSI team. Yeah, so thank you for joining.